Hello everyone, welcome to Automate with Kaj, where we simplify industrial automation. Today, for our tutorial, we'll be working with a Mitsubishi PLC to work as a Modbus RTU master. Okay, so we'll work with the Modbus protocol. You used it with Control Edge in the last video. Now we're going to use it with Mitsubishi PLC. The PLC of interest will be the Q series CPU with the Q mode. Mitsubishi has different models of PLCs. We have the FX PLC, we have the LPL series, different types. You can go to their websites and you'll see the different PLCs. For us, we'll be using the Q series PLC. Now, this PLCs it's a modular. It has a modular architecture. What it means is that there's a backplane, okay, a backplane where we can slot individual modules like the power module, like the CPU module, and another module which is of interest to us for this course. So the tools we'll be needing for this course, we'll be using one of the models of the Q series PLC, which is the Q03UDV CPU. Another tool we'll be using is the QJ71MB91. This is another module, and this is an RTU card or a serial card folder, which will be very important for us for our communication or for our setup today. We'll be using GXWorks 2 also, which is the environment for programming the Q series PLC. There's also GXWorks 3 for other brands or for other models of the Mitsubishi product line. We also need connecting cables, preferably twisted pairs, your writing materials, and your attention. So let's get started. So for this tutorial, the QJ71MB91, I'll be calling it MB91, okay, because to call all that, it's a mouthful. So anytime you hear me say MB91, I'm talking about the module QJ71MB91. It is a serial communication module. So we're going to look at the physical connection first of all, okay. It's important to know the physical connection because this is this is the deciding factor, all right, for if your setup is going to work or not, or if you're going to damage the system. We do not want that to happen. That's why this is very important. So now here is the model. This is how it looks like. You can see the model number at the top, QJ71MB91. And as you can see from this picture, I want you to look at it, digest it, see what is there. Maybe take a note of what you observe. Yeah, I know I've had it all written out. Okay, so as you can see, we have two channels, okay, channel 1 and channel 2. And channel 1 is a serial RS232 interface, and channel 2 is RS422/RS485. I'm going to discuss in details what these interfaces are and how they are to be used. Okay, it's important to know them so that when you're in the field and you are faced with this, you will know what to do. So we're going to start with channel 1, which is RS232. RS232 is a widely used industrial standard serial communication interface for point-to-point, full duplex, asynchronous data exchange. So typically you see it as a DB9 connector. As you can see, this one is a DB9 connector. When you count it, see that there are 9 openings for you to use. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, DB9. Or there are also what you call DB25 connectors. So it enables reliable short-range communication at a distance of 50 feet up to 20 kilobyte per second. Okay, that's the baud rate. That's the highest baud rate that you can attain with RS232. One of the features of this interface, all right, is it allows asynchronous communication. Okay, it does not require shared clock signal. It is framed with start and stop bits, and you can communicate simultaneously. So you can send and receive data at the same time. You don't need to send and wait before data is received. So it does it asynchronously, send and receive at the same time. Point-to-point communication, you can you have one master and one slave. So you have the master, okay, on one side and slave on the side. So you cannot have more than one slave on the RS232 serial network. Okay. Flow control, which you can use to manage the flow of data along the transmission line. So for the hardware, you have the ready to send and the clear to send. So ready to send, when you ready to send, what it means is that the slave device sends a feedback to the master that okay, I mean rather the other way. The master device, okay, after sending data to the slave device, okay, it gives a feedback to the slave that I am ready to send new data to you. Okay. Now the slave device needs to be ready to receive that data. So it sends a clear to send signal. So once this cycle is complete, the master device sends communication to the slave device. Okay, I hope that is clear. Then we have the DTR and the DSR, which is data terminal ready and data sets ready. On the software side, you can also do software flow control, X on and X off. For signal distance and speed, the recommended max cable length is 50 feet, which is 50 meters. So the more the distance, the lower the speed you use, because if you increase the speed, you increase the chances of noise on the line. And for connectors, primarily use the DB9 or DB25. So this is the terminal pinout for our DB9. Now this is peculiar, or this mode of connection is peculiar to Mitsubishi. If you're working with other types of DB9 on another module, it's important you check the data sheet of that module to know how it is connected. Okay, so pin number 1, it is completely prohibited, not to be used. Number 2 is reception data. This is what's used to receive data from a target device. Okay, and this is to be connected to the TX of the target device, the transmit connector, the target device. While the SD is to transmit data, to send data, and you connect it to the RX or RD of the target device. Pin 4 is not to be used at all. Pin 5 is signal ground, and this is to be connected to the target device signal ground. Pin 6 not to be used. Then number 7 and number 8, these two are to be linked together. They're the ones who starts the communication, the start or stop. Then number 9 is not to be used. So let us keep going. So let's move to the next one, channel 2, RS422. And this is a high-speed differential serial communication standard designed for long-distance reliable transmission in noisy environments. It supports distance up to 1.2 kilometers, data rate up to 10 megabytes per second, and full duplex 4-wire communication with one driver and up to 10 receivers. So RS422 is an upgrade from RS232 because of the limitation of our RS232. We can use RS232 for long distances. So RS422 was created to solve that problem. It also have this full duplex setup where you can both send and receive at the same time. Okay, and some of the features that are listed here, differential signaling. Okay, what differential signaling means is that one pair of the cable, all right, one pair of the transmission line will have a positive voltage, and the second pair will have a negative voltage. So the target device sees the one with positive voltage as a 1, while uh, the other one with negative voltage sees it as a 0. So no matter the amount of EMI in the line, it doesn't have an effect. So far the top one is a positive and the other one is a negative. It's always it as 1 and 0. So the network configuration is typically a 4-wire for full duplex. Okay, so you can do, like I said before, you can transmit and receive at the same time. You don't need to wait for when you send, you don't need to wait for the send to be completed before you receive data. For the low capacity, it supports one driver and up to 10 receivers. At the end of the network, you need a terminating resistor to minimize reflections, and it's commonly used in industrial automation, factory environments, and long distance networking. So here is a picture of a typical connection on RS422. So you can see in this picture, okay, you have your master device and your target devices. We have 3 target devices here, and if you look carefully, okay, T plus T minus, by going to the R plus R minus of your slave device, and the R plus R minus to the T plus T minus of your slave device. Okay, so you can see now from this drawing, you can see, let me point it out. Okay, here I can transmit data. Okay, I can transmit. When the signal goes to this line, you can transmit data to all these guys. Okay, at the same time, I can receive data from any device at the same time without having to wait. Okay, so transmission goes this way, reception goes this way. Okay, at the same time. I think that's very cool, okay, for the RS422. So asynchronously you can transmit data. Okay. So for our QJ of our MB91, all right, this is how we can connect it. Okay, so like we saw in the previous picture, we have about 7 terminals. The top ones are SDA, SDB, which is our T plus and T minus, our transmission terminal, which will connect to R plus and R minus of our slave device. Then RDA and RDB is our R plus and R minus, which will connect to the T plus of our slave device. And you can see the direction of transmission of communication. Okay, SDA is going to R plus and it's going the other way. Okay, so the next thing we'll talk about is RS485. Okay, RS485. It's a standard for balanced differential serial communications that allow multiple devices up to 32, and you can get up to 256 devices when you want to add more devices after 32, you have to use repeaters. You can use to communicate over long distances up to 1.2 kilometers, and it's very resistant to industrial noise due to differential signaling. Remember, we talked about differential signaling in the last slide, where you have a positive voltage on one cable or on one pair of cable and negative on the other pair. You also have multi-point bus topology, supports up to 32 nodes on a single bus, extendable to 256 or more repeaters. You can have long distance of 1.2 kilometers of transmission, but the longer you need to transmit data, the lower the speed, okay, because of noise. It operates using half duplex. Remember I talked about full duplex for RS422. It means I can transmit and receive at the same time. It is different for RS485. There's a diagram which I'll use to show you why. Let me just quickly explain. The half duplex operation means when you send, you have to wait. You can't send and receive at the same time. You have to send first and receive. Okay, so like a queue, one has to happen before the other. However, it is simple to implement. It requires just 2 wire plus ground for communication. So here's a simple picture of RS485. So you can see for the red cable which I terminated to A over slave device, I looped T and R plus, okay, and then I looped T minus and R minus on the blue line. So you can see that you cannot have the two happen at the same time. Okay, one has to go before the other. At the end of the line, there's a terminating resistor. It's very important. Okay, so the key features: 2 wire. Oh, this is half duplex. Half duplex up to 1.2 kilometers. Supports 32 devices, expandable to 256 using repeaters, and also 10 megabits per second baud rate for short distances. So peculiar to our device here at the MB91, like I mentioned, SDA is our T plus for transmitting data to a target device. T minus is the same thing. Then RDA, R plus, RTB, R minus. Then SG, signal ground, and FG is a frame ground. Here is a drawing of how to do the connection on a slave device. So if your slave device is looking like this, if this is how the terminal is, this is how you connect it. Okay. And the same thing, you will link the SDA and RDA, SDB and RDB. So now we're going to move to Mitsubishi software so that we can uh, configure it on software. Now we've done the hardware wiring already. So now let us write the program for communication. So this is the programming environment for Mitsubishi PLCs. GXWorks 2, there's also GXWorks 3. For exercise, we'll be using GXWorks 2 today. So for us to get started, create a new project here. Okay, Control N, or you select this. Selecting your CPU. This depends on the kind of CPU you're using, so you need to check your CPU very carefully. Okay, remember I mentioned that there are different brands of CPUs to use. For this project, you'll be using QCPU Q mode. Now there's another one called A mode. So QCPU. Then the type. Make sure you check the model of the CPU you're using and select it to avoid any conflict. The project type, we'll be using structured projects and structured ladder slash FBD, meaning that we can be able to program or write program with both function block diagram and structured ladder. Click OK. So now with our projects created, we have our project tree here, okay, which we can configure based on our settings that is needed. So the first we'll be doing is parameter. So we're going to set our PLC parameter. Give our PLC a name. Let's call it we are not going to do anything here. We won't do anything here, 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 nothing. Keep in mind this this area, we're going to talk about it a little later. This is very important. IO assignment. This is where we're going to. Now remember I mentioned I mentioned earlier that this PLC, this QCP, they are modular in nature. Okay, they are modular in nature, which means that we have a back plane, all right, with plugs where you can plug in different modules like a power module, a CPU module, an input module, output module, to name a few. Okay, and Modbus serial module. So this is where we build that module, all right, and set it up here. Then once we're done, we download it to the PLC so that the PLC knows where exactly it needs to scan. So the first thing we need to select here is our PLC. Okay, so select PLC type. Remember CPU and then the PLC type. So since we're working with only our serial module for now, we'll just select here new module. We're looking for this module, Modbus interface module. Now this is MT91. This is for Modbus TCP, or this is a TCP card, and the MB91 is RCU card, serial card. Notice this address here. Okay, so this address means the position, the address of the slot where it occupies. Okay, and this particular module occupies 32 points. Each individual plugs on the rack gives about 16 points. All right, some modules can take up to 32. So when it takes 32 points, okay, it's as if it's taking 2. All right, but on the software side, okay, but not on the hardware. Okay, you can see 32 points. And what do I mean by on the software side? So now the address is 0000. This is the location, okay, of the address. So when the PLC is scanning, it wants to scan what's happening on this card. It comes to this address and scans this address, okay, during its scan cycle. Now let's imagine I have another card here. Let me say I want to put an input module. Now if you see the address, you can see 0020 because the MB91 has taken 0000 and 0010. Okay. Now let's say for example, let's imagine now let's put an input card here. All right, so that you can see what I'm talking about. So let's imagine we put an input mode here. We see that it's taking 16 points. Okay, 0000. So it take only this point, it's not going to take another one. So when we select this and we'll come here to add another module, you can see that you have 10 here, 0010. Okay, so I hope that is clear. But we are not using an input module. Remember, we're using the Modbus interface module. So select this, I'll select MB91. Remember, it has taken 32 points. Mounted slot is 0. Yep, we are replacing it. Yes, so that's 2 points. Okay, but the slot is still slot 1, but the address now has moved to 20 if you want to add another module. Okay, so what I was meaning to say is that it has taken 2 addresses, okay, for the CPU rack, 2 addresses. Okay, so this one has been settled. We'll go to this. Please take note of this IP address, it's very, very important. Okay, this is the default IP address for the CPU, 192.168.3.39. So we check, make sure there's no error, and then we end this setting. So that's that for this particular setting. Let us save our project. So click on new project, save as, give a project a name, tutorial. Click save. You can give it another name, just choose this very simple name. Now this is showing this because of the, I've chosen it earlier and I changed it. Okay, so you can just delete this. If you have this on yours, all right, and you notice this, you can go to your PLC parameter and check why. What it means is that this doesn't exist. Okay, so you can just delete it. Yep. Okay, let's start with configuring our module. Now we selected the module, we need to configure it and set it up for communication. So we have switch setting, automatic communication parameters. Okay, so these parameters to ensure that the module is able to communicate with other devices, multiple device assignment parameter, and auto refresh. So for our tutorial, we're working on this setting, and this setting. I'll explain what each one does. So let's go to switch setting. So hope window comes. Now remember, I discussed the other time that we have channel 1 and channel 2. And channel 1 is for RS232, channel 3 is RS485. For our tutorial, we are working with the RS485 side. So first of all, we need to set the mode, the setting. So we want our device to serve as a master, so you can leave it at the default, okay, without having to change it. Then the next one is device assignment parameter. Now we have 2 selections here, default parameter and user setting parameter. So this default parameter, what it does is that it's the PLC, when it's working, when it's scanning to look for program to work with, it can, for this specific project, for this specific purpose, it is either going to look inside the POU, okay, for the communication program, or it's going to look into the automatic communication parameter. Okay, so for the POU, default parameter will look into the POUs when you set the default parameters, but when you set it for user setting parameter, it's going to look at the automatic communication parameter. So keep that in mind. So we set data bit to 8, parity to none. Okay, since we set parity to 1, we don't need to change the type of parity, whether it's even or odd. Stop bit is 1. Frame mode, we can select either RTU or ASCII. We're using RTU. You can leave this. Then your baud rate. This baud rate is dependent on your slave device. So if you have like 4 to 5 slave devices, and the biggest baud rate is 15200, and the smallest one is 9600. First of all, what you need to do is all your devices, you have to set the baud rate to the baud rate of the smallest device. So let's imagine the limit of the smallest device is 9600. You need to set all the devices to that same baud rate, so that, and the master, you set it to that 9600, so that it can be able to communicate with all your devices. Then your station number is 0. Your master address has to be 0. It cannot be 1. Okay, if you set it as 1, we're going to have an error. Okay, so set it as 0. But if in the case where I set it as a slave, okay, where I set the module as a slave, I can now change this to 1, and this will be the slave address. But for our function, we are working with master, so set this as 0. So click OK, and that setting is complete. Let's make sure to always save our work. Then we'll move to the next thing, the automatic communication parameter. As you can see, you have channel 1, you have channel 2. Okay, so there are individual parameters which can be set. The first parameter is setting existence. Now, in this place, we have about 32 automatic communication parameters. Okay, 32 automatic communication parameters or settings. All right, so you can use all 32 for your process. Okay, so if you have 32 slave devices, you can use all 32. I remember I would mention that for RS485 specifically, we can talk to how many devices? 32. Okay, so for this setting now, this number 1, we want to activate this number 1. We can actually use any other setting. Okay, we can ignore this, and go to setting 3 and activate it. But for the sake of uniformity, we'll start from 1. We'll activate it. The setting is existing rather. 1. Target station number is the address of your slave. Okay, so you have to confirm that, what address, or you have to set it on your slave device. For this tutorial, we're going to use 1. The request interval. How often should the master request for data? Okay, do you want it to be consistent? No timer, it just keeps requesting. You can leave it at 00. Okay, but if you want to have a small time gap, you can set it. So for Mitsubishi, the time here, if you want to set for 1 second, we know that 1 second is 1000 milliseconds. But for Mitsubishi, you divide that value by 10. So that's 100. That will give you 1 second. And this, the response time delay. So what is response time delay is like I usually describe it as a watchdog timer. After a first request from the master, after 500 milliseconds, if there's no response from the slave, it's going to trigger an alarm that there is no response from the slave. There's no response at all from the slave. Okay, and you'll be able to see that alarm in diagnostics. Okay, you see it in diagnostic system monitor. And the next thing is type specification of the target device. So what data do you want to read from the target device? You want to read analog data, you want to read digital data. For Modbus, we have 4 types of, let me just call it data. Okay, you have read coil or read input coil. The second one is read, you can see it here, read coils. Yes, read discrete inputs, read input registers, read hold registers. So these are the read specifications. Okay, then the next one is write. You can write to a coil, you can write to a holding register, or you can do a read write. For our own function, we're going to be reading holding registers. Now, after whatever setting we select here is what determines which particular setting between read settings and write settings will come on. If you're going to we're going to be in a read, okay, the read setting is what will be activated, okay, for you to be able to configure. If we're going to do a write, I pressed enter just in case. If you're going to do a write, the write settings will be activated. If you're going to do a read write, both comes on. Okay, that's for holding registers specifically. So for our tutorial, we're using the read holding registers. Now, our read setting, the first thing they ask us to do is the head buffer memory address. What this means is the MB91 card has memory location where that data you have read will be stored. Okay, that is this value you want to add here. Okay, the memory location. Now this is in hexadecimal. So for you to use it, you need to have your calculator. So we're going to bring a calculator now. We're going to use the programmer calculator. Okay, so we are starting with address 0. So I'll put 0. Remember I said it's hexadecimal. So the hexadecimal value for 0 is 0. Okay, that is number 1. Keep that in mind. Number 2, now if I select this, If you look down, you're going to see an explanation here of what you're supposed to input in this place. It says specify the head address of the buffer memory where the data are read from or written to the sleeve are stored. The head buffer memory address should not be duplicated among communication parameters 1 to 32. So whatever address you put here, you cannot put that same address. So imagine I put 0 here, I cannot put 0 here. It's not going to work. Okay, because you can't put two different data on one addresses. You have to separate it. Do you understand? Now, what does it mean? What are we going to put now? They said 000H means non-target reading. So this one means that you're not putting it anywhere. Okay, this you're not putting it anywhere. But when you have 1000H to 1FFH, they use this as an example. It means channel 1 side reading data storage place. So 1 is channel 1, then the remaining 000 is the location where you will be putting the data, and it stops at FFF, which is about 255, so about 8 bits of let me just call it 8 bits, 256 address space that you can put your data. Okay, but now remember I said this is 1 for channel 1, so that means for channel 2 that will be 2. Start from 2 meaning channel 2 and the address location. So we're going to start from 0 like we said, that will be 2000. Okay, that's not 2000, that's 2 and address 0. Okay, so in layman language 2000. Okay, so our target Modbus device head number is where our slave device, the data we're reading for our slave device, where is it located? Okay, on the register address, where is it located? So that when the master wants to ask for the data, it goes specifically to that address, okay, and pull the data from there. So it says specify the head number of the read or write target Modbus device. Now pay close attention to this information. It says as a target Modbus device head number, set last 5 digits of actual device number minus 1. Okay, minus 1. What does this mean? So it means that if the memory location, all right, of your data is in, let's say the address the position is in number 50. Okay, it's number 50. You have to give an offset of minus 1. That will be 49. So that 49 is what you're going to put here. So this address that is going to be here will be always be minus 1 of the original position where the data is located on your slave device. Okay, so here's what I mean. Here's what I mean. If my address now where my data is located is in 25, when I want to slot that address inside here, I have to remove 1, give an offset of 1. So that means my address, my start address, my target moving device head number will be 24. Okay, very good. So now let's imagine let's our slave device is going to start from 1, and then if we take an offset of 1, it's going to be 0. So our head number is going to be 0. So that's 0. Access points is the number of data points you want to collect. So if say in your slave device you have 20 data points, that's what you're going to put here. So 20. Let's use that. So that's that for this parameter. Okay, parameter 1, we've done for parameter 1. Now let's do for parameter 2. Okay, you know what this is. For this, we'll maintain it at 0 because this value covers for every other one. Okay, and then request for that time we use 50. Sorry, target station number. This is what this is. So that will be 2. This will be 0. This will be 50. We're going to read coils for this one. And then let's read input registers. My slave device don't have coils, so I'm going to read the registers. Okay, now I said I've read from 0 to 20. Okay, so I'm reading 21 data points. Okay, 21 data points. So that means from 0 to 20, that's 21 spaces has been collected. Okay, 21 spaces has been collected. 0, 1 to 21. So the next available space will be 22. Okay, 21 is no longer available because from 0 to 20, this is not 20 minus 0. Okay, it means that at position 0 there's data there to position 20, and when you count it, that'll be 21 spaces collected. So the next space is going to be 22. Okay, so now this way we're going to put here is going to be 22. This data I want to read into parameter. I want to read from parameter. I want to store it in address 22 of the serial card, the MB91 card. And when we do our calculation with our programmer calculator, the hexadecimal for 22 is what? 16. You can see it. Okay, so now we're going to write channel 2 address 16. Okay, very good. So our head buffer address, we can start. Let's assume that we'll be using this value. Okay, 0, and we're collecting 20 data points. All right, good. So let's work with only 2 parameters for now. Okay, 2 parameters. So the next spreadsheet we'll be working on is the auto refresh. Auto refresh. Okay, so what this auto refresh does now is, or the simple meaning of the auto refresh is, I can transfer data from a module to my PLC, or from a module storage, all right, that is on my PLC rack, or my Mitsubishi PLC rack, to the storage of the PLC, or I can transfer data from my PLC storage to another device within the same rack. So in my case now, in our case, we're using the MB91. So I want to transfer those data I've pulled that is in the storage of the MB91. I want to transfer it to the PLC storage so that I can use it. So that's what this first is all about. Automatic function buffer input. So I double click here. Where do I want to store this data now on my PLC? I want to transfer this data to someone, a data storage location on my PLC. Now remember where I said you should take note of when I was on the PLC parameter. We're going to go there. Okay, so I can cancel parameter. I go to, nope, I think to the device, yes. Now, all these values that are here are memory locations, okay, for where data can be stored. Okay, they are memory locations. Now, the memory location of interest for us is data register. Okay, data register. This is where I want to store the data I receive from my PLC. Okay, from my MB91 card D, and I have up to 13,000 device points. Okay, very good. So now I go to auto refresh, I double click here, and I D0. Okay, I want to start from D0 because remember I said I have 13,000. I'll put 0. I'm collecting about 42 data points. Okay, 21 plus 21. Remember 0 to 20, that's 21. So I'm collecting 42 data points. So I just want to transfer the value since from 0 to 42 to transfer it to the PLC memory. Okay, so this is the only places I want to use. Now take note, if you put more than, let's say you put 50, okay, those address spaces where you've used, you cannot put anything inside there again. So you have to be careful when setting this. So put it so click OK. So that's for that. So it's completed. Compile our work, or rebuild all. This is a new project. Click rebuild all. Save our work. So that's simply the way to program, to write a PLC program. You connect your PLC and then you write to it. So in the next tutorial, okay, we'll download this program into a PLC with a real slave device, and then we'll see it work. Okay, thank you very much.